Tremblay. Marc graduated got his PhD from UCLA a few years ago. He's been working at Sun since he got his PhD, I think, and did a lot of interesting projects. There was a Java processor project. It was the Magic processor. It was a new instruction set architecture for graphics and things. It had a role with Java, I believe. He's been involved in the UltraSpark 1, right? UltraSpark 1, Sun's had this history of some of its processors have been extraordinarily successful. UltraSpark 1 was one of those extraordinarily successful. What he's going to talk about, and he's now a vice president, and as well as a fellow is a technical honor for his contributions, and he's also a vice president, which companies have. The fellow is the valuable part of that title. So what he's going to talk about today is, I think, one of the really exciting things that have happened in computer architecture in this era where performance isn't getting any faster due to power problems and memory latency problems. Sun took this radical bet on trying to build a whole bunch of simple processors on the chip, and they made this bet several years ago, and the bet is being called starting this month, and so Marc's going to be able to tell you about that.
How about that for an impromptu intro? We recruited the right person. So good afternoon. I have lots of material. I actually thought we had an hour and a half, so I will go and cover it as quick as possible and skip the marketing part. In the 80s, the old guys like us remember on com.arch, the attack of the killer micros was the hot topic, that microprocessors were going to take over the world. Well, they did, from laptops to supercomputers. Our thesis for at least the second half of the decade, and probably beyond that, is that it will be the attack of throughput computing in all computer segments. It's hard to argue that there's not much thread-level parallelism on the server side. All the scale-out implementations out there. The internet is massively parallelized, right? Google is running hundreds of thousands of threads simultaneously. Even a desktop, the emergence of dual-core, quad-cores, will lead to a lot of cool software that will be accelerated. And it's hard to find applications in the supercomputer space that don't have TLP. We've shown this chart quite a few times, showing that if you analyze benchmarks on the server side, which is our main focus, right? At times you encounter ILP. Instruction level parallelism, where you attempt to parallelize things at a very fine coarse granularity at the level of instructions, while thread level is a much coarser granularity, explicitly in the sense that the programmer has specified course or blocks of code to be executed in parallel. And you see the high across all benchmarks here. So strangely enough, our industry has mostly been using desktop-style processors and desktop-style benchmarks to drive the computer industry. And I expect the next several years to see a pretty drastic divergence between these two types of architectures. So, I'll skip this one. But so, very simple idea behind multithreading. Multithreading has been around for a while. But the main observation is that if you look at a server, and we have 10,000 of those in Sunnyvale in our ranch, and we're very proud of the fact that 98.2% of the time, each processor is running something. So if you do look, yes, they are busy, but they're busy running a process. But if you look a little bit more closely, they are busy 15, 20% of the time computing, and they wait for memory, because memory typically takes 300-400 cycles. So the rule of thumb running a database app is that you have one miss per 100 instruction, one load miss. So every 100 instructions, think about going to main memory, accessing main memory, coming back later, 400 clocks later. So instead of just being idle with this pipeline, this processor pipeline, we would like to switch thread in 0 time, effectively, and then run this second thread and eventually run a 4th thread, because this one also has to go to main memory, this one has to go to main memory, and then the 4th one. And by the time the 4th one has to go to main memory, hopefully the data has come back from the first one, and this one can compute and continue. So notice that there's only one pipeline here, so this is collapsible, and this would be blue 100% of the time. Perfect example. You would have 4 times utilization for slight area increase, which I will quantify soon. We've been at this for a long time, as Dave was mentioning. This is a slide I showed in 1999, talking about throughput computing, talking about everything I've discussed so far, and then showing the vertical threading that was supported. Niagara is our first drastic implementation of this, and because we've architected the core to support this and not support tremendous instruction level parallelism, we're able to have 8 cores on a single piece of silicon in 90 nanometer. So as you can see, there's a lot of stuff going on here. There's a lot of blue because you would collapse this. And whenever I mention a thread, by the way, I also mean a process. So these could be 32 different processes. So that's defined throughput computing is the aggregate amount of work done by all cores, all threads, all functional units. The most misunderstood thing, and I probably talked to hundreds of customers about this and colleagues and engineers, is the fact that you don't need multi-threaded software to take advantage of this. If today somebody is running server workloads on a 32-way SMP, it will run just beautifully on this, right? So you can have, yes, you can have an Oracle app that is multi-threaded, or you could have something that you will attempt to parallelize with a compiler, or you could have multiple copies of an app server, let's say from BEA, and each one scaling to, let's say, 6 threads and have 5 copies of that application. The worst case is you have a large monolithic application that has a single thread that's not parallelizable, and you're stuck with that. Well, you may still be in a throughput computing mode. So in our ranch, VCS, which is a very large accelerator, is probably our #1 application. Well, we can still have 32 copies of this. Solaris will only maintain 1 in physical memory, so you're saving the physical space, and then run them in a throughput mode. So the only examples that don't fit this model is, well, you have that same application, let's say, and you really care about turnaround time for that one instantiation of the application. You're sitting on your desktop and say, I want to simulate this big processor, and I'm waiting for it. So if that's the case, that's not your ideal scenario. If the case is you're sending 10,000 simulation jobs to run this, that's a throughput computing problem. So it puts everybody on the same level. What does a typical chip multi-threaded processor look like? Well, I will re-emphasize it later on this point, but we started a multi-threaded core designed from scratch, sharing an instruction cache and a data cache, going through a switch, going to a second level cache, going to a memory controller. So those are the basic blocks. And then literally, we just copy and paste this. And on Niagara, just happened to have 8 of these. And because we want a global address space, the switch is actually a global switch. The L2 logically is shared as a shared memory. And then you shared memory controllers as well. So this is interesting. You have a nice chip, but boy, we quickly, you attach DRAMs to this, and you quickly run out of bandwidth. So what you do is you actually physically bank the L2 caches and the DRAM as well. So randomized animation. So you end up with, logically, you still have one main memory, logically one L2 cache, but we bank it so we can do several reads and several writes simultaneously in the same cycle. So in the industry right now, big debate, should we put the memory controller on chip or off chip? Well, obviously in this particular scenario, if you're going to have, now the memory subsystem has 32 different customers, we have 4 on chip memory controller by 16 bytes. So massive bandwidth coming in and out of this this NAG, or UltraSpark T1, as I guess is the formal name. Okay. Well, we'll try something else. So the impact on the microarchitecture is that if you want to be able to context switch rapidly these threads and processes, you have to save the state on chip. Right? And most of the state is in the register file. And that's okay. So all in all, if you look at quadrupling the content of the register file, quadrupling some of the control registers, a core maybe grows by 20%. And the chip itself will grow a fraction of this, maybe 10%. And it's not linear. Once you've put the real estate and the state machine for 2 threads, going to 3 threads is not twice as much logic. So it starts plateauing. More importantly is sizing the memory subsystem, because now you're banging at memory a whole lot more often. So more outstanding loads, more outstanding stores, deeper buffers, the capability to differentiate between threads in the iCache, data cache, and TLB. And a note on power, we find out that now the processor isn't that idle anymore. So average power tends to be very close to peak power. Well, that's good. And let me show you a chart that the gentleman from Lawrence Berkeley National Labs did. And I just ran across this. This was actually the utilization of a Dell PowerEdge. It could be a Sun computer over time. And same thing. Notice that when the computer is idle, the heat dissipated by this machine went down slightly. So the shame is that, well, that would be just fine if the heat went down as well and the power use was going down as well. But you've already paid for the heat sink, the cooling systems, the way we size fans and the RPM of the fans, the way we put the reason why we only put 2 in a 2-use systems. Wouldn't it be nice in our environment, we're not after saving energy as much as being very efficient with that power. So wouldn't that be nice that if during idle time you were able to run other threads, other searches, other Oracle threads, so that, yeah, okay, you'd be dissipating a little bit more heat, but you'd really take advantage of that, that average utilization. Mentioned the impact on the memory subsystem. Now, we talked to customers, and so far this is a broad market for us. An interesting dilemma is that, boy, we'd really like this extreme throughput, but we'd also like to have very powerful nodes so that we get better turnaround time. We get around Amdahl's law to a certain extent. And you look at this and say, well, so far people understand how you can do that. You can simplify cores and attack multi-threading to the extreme. But how do you provide also high single-thread performance? Very conflicting vector from an architecture standpoint. So what we're going to try to do is, our major vector is throughput. So you better have small cores, low-power cores that can easily be threadable. And because of power reasons, because we're going to put tens of these on chip, you can't rely so much on clock, because that's not the most power efficient way to deliver performance. The second vector is providing high single thread performance. And the rest of this talk basically covers with some of the secret sauce that we have that will deliver both extreme throughput and better single thread performance than we see today. So back to the dilemma of instruction level parallelism and thread level parallelism. TLP is a huge leverage for performance, but let's not forget Amdahl's law. And if I can summarize it, if a piece of code is 20% serial and 80% parallelizable, it doesn't matter if you have 1,000 cores, you'll still only speed it up by 5x, because there will be that serial section that you cannot accelerate if all cores are equal. We run in for large commercial software where there's actually data sharing happening. Well, there are synchronization issues, there's data sharing issues, scalability issues. So all of these, we feel, need to be addressed by providing the right amount of instruction level parallelism and thread level parallelism. So what we did is, we're going to study a whole bunch of cores, a variety of threading model, and see what each one gives us. So let me just show a chart here, the first chart. So we simulate basically two very different types of cores. One is called a lightweight core, and think about it like a core that's in the Niagara chip. So that's a single issue machine. There isn't even branch prediction. Moderate clock rate, we announced 1.2 gigahertz. It's not exactly this core, but it's very similar to this. And when we simulated the server workload on this, going from one core to two to three, well, 1, 2, 3, 4 cores provided 3.6x better server level performance as a single thread processor. As we increase the number of threads on this one core processor, with 4 threads we were getting 3.2x speed up. Amazing speed up, right? And then similarly, if you look at 2 cores, each one with 4 threads, you get 5.5x the performance of a single core, single thread. Notice that one core with 4 threads is higher performance than 3 cores for really a fraction of the area, right? So I'll make a comment on the state of multi-threading in the industry. So far Intel has claimed between 0 and 20%. Some customers see minus 5%. That's okay. And it's very hard to bolt multi-threading onto an existing pipeline. It's certainly very hard to do that on a Pentium 4 pipeline. Fujitsu claims up to 20% on their SPARC 64.6. It's vertical threading. They flush the pipe when they switch threads, so not surprising that you don't see a big number there. Power 5 and Power 5 Plus have a better threading model. It's SMT, pretty nice implementation, but it was also done after the fact, after building Power 4. They gain up to 40%. I'll show you data later on that on some commercial workloads, we see a factor of 3x from 4 threads as opposed to 1 thread on Niagara, because it was built from scratch. So fast forward 2, 3, 4 years from now, I'm convinced that any new core from the rest of the industry will have multi-threading built in. There's just too much server level performance there to ignore that. Notice that 4 cores, 4 threads delivers 10 times the performance of a single core, single thread. Very attractive benefit. And there's a slight tapering off going from 2 threads, 4 threads to 2, 3, 4 threads, but it's still a huge benefit to go to up to 4 threads. Now let's go to a heavier core. This is a multi-issue core with your favorite branch prediction, some speculation happening as well. So now going from 1 thread to 2 threads, so a huge benefit, 50%. Going to 4 threads kind of saw the same ratio, so 1.4x. So not as steep as we saw before, but remember, this is probably for 10% increase in area and another 10 for another 2 threads. So for a total of 20% at the core level area, you easily double your performance. Even with these beefier cores, we were able to, if you just replicate, if you have the real estate in silicon, you're able to almost quadruple the performance with 4 cores. So diminishing return here, obviously you'd go to 6, 7 threads, your pipeline would be full and saturated. But certainly interesting in the 2, 3, 4 threads here. Now the $64,000 question is, well, that's great, but what was the ratio in performance between these 2 cores in terms of performance, area, power? And I'll tell you, in terms of performance, there's sometimes a factor of 4 up to 10x between these 2 cores. The cores are bigger, they dissipate more power, they take more people to implement, but it's all workload dependent. It depends what we're after from a target market perspective. Now let me just spend next 3 slides just describing what Niagara is. It's not meant as an advertisement, just to put things in perspective. 32-way SMP, 8 cores, 4 threads per core, dissipating less than 70 watts. So that's why we actually launched the chip 2 weeks ago in San Francisco, and under the banner of an eco-responsible thing, because you end up saving a lot of power doing this. If you look at, we will be introducing metrics that measure performance, space, power, as to enable people to really measure what's the benefit of such an architecture. Believe it or not, in the commercial space, power, both supplying the energy and taking the heat out, is easily 25 to 45% of the budget of running a computer room. I'm sure it's kind of the same here. Now, numbers that we've never made public until now. So this is a thread running on Niagara. And for those not familiar with CPI, clocks per instruction, says how many clocks on average you spend per instruction. Mentioned this is a single issue pipe, so you start with 1. So if everything went well, you would spend 1 clock per instruction. So let's look at 1 thread. Unfortunately, you have instruction cache miss. This is running Oracle, a large application, in a small 8 kilobyte cache. 8 kilobyte cache. You do miss, so you just added on average an extra cycle, 0.17 per instruction. We have data cache misses, L2 cache misses. At the end of the day, you end up running Oracle. You spend on average 5 clocks per instruction. Not too exciting, not abnormal either. Now let's put 4 threads on this core. And what happens on a sync for that 1 thread? Well, you see that now, because all 4 threads share a pipeline, there's round robin, and you actually sit in your instruction buffer, once in a while, which wastes half a clock per instruction on average. The iCache miss rate has gone up. So yes, we claim that there's sharing at the instruction level and data cache level, but you're saving a lot in sharing, but there's also displacement and some pollution. So that has gone up. Data cache miss rate has gone up. L2 miss rate has gone up. So you add all of this up, and now you're spending more clocks on average per instructions for that single thread, 7.2 as opposed to 5.3. But you're running 4 in parallel. All right, so divide this by 4, you're down to 1.8, and here's the factor of 3. The per core CPI has gone down by a factor of 3 while running 4 threads. So you're able to run 3 times as much transaction in the same amount of time. The power advantage of doing something like this is actually a die photo of AltoSpark 5, which we actually ended up canceling because it was the perfect example of a big monolithic implementation. Single pipeline, was actually supporting 2 threads, 6 issue, very aggressive out-of-order execution engine. Look at the power, the heat being concentrated in the integer unit and floating point unit, versus if you build a CMT, you inherently spread out the heat and end up with something a lot cooler. So we've announced the chip systems are rolling out and will be shipping in volume in the next couple of weeks. Now, I've mentioned Amdahl's law. Here's a chart I took from an Intel paper that was shown at ISCA. Running, if you call them somewhat more high-performance computing apps, but it shows the percentage of the sequential component for some of these apps, right? So your favorite BLAST, TPCH, SWIM, and you see a significant number here, going from 60% all the way down to 5%. So when we simulate these cores and the amount of sharing and lock optimization that they have, we have to keep that in mind, because I'm showing here, once again, our 2 favorite cores, the light core and the heavy core. And in this particular case, the heavy core was starts off almost 5 times faster in terms of single thread performance. So this is time spent, so the lower the better. So as you add threads on this parallel program, assuming that it's 99% parallelizable, you see that, well, with threads, of course, the execution time with light cores goes down, but it takes roughly 6 threads to achieve the same time as you had with that single powerful thread here. And of course, you scale that as well. This is with a 1% component that's not parallelizable. If 10% of the application is not parallelizable, boy, now you need 16 threads to catch up to this powerful single thread performance engine. And if it's 20% sequential, you never catch up because 5x is the maximum you could achieve. So it puts in perspective what's the right balance again between a single powerful core and an army of them. So how are we going to do this? We don't benefit from easy transistor speed up as we did in the past. Just jacking up clock, even the process was given us that increase in performance, it would be questionable if we were going to do it, because you still would need a deep pipeline, which becomes very power inefficient, because not only you have lots of flip-flops, but the deeper your pipeline, the more time you actually spend in flip-flops proportionally. So the percentage of cycle time spent outside of the setup time going to the flip-flop and hold time is less and less proportionally. And to handle a deep pipeline, you have to have more sophisticated branch prediction. You have to have maybe a trace cache. So really is a vicious circle here. Doing speculation in space, providing multiple adders, let's say, to get the lower order bits to access the cache ahead of time, very costly in terms of power. And it's also, you're sending speculative accesses, which means that you have to provide more bandwidth than in the non-speculative case. So we are benefiting from a great process. This is just a picture in 90 nanometer, and we're done with 90 nanometer, but shows all the copper levels and the high K dielectric. What hasn't scaled so well, of course, is the thin oxide at the gate level. So as we scale down the process, that's not scaling as much, and now that's at the level of a few atomic layers, and that's why we have this power issue. So everything we're doing right now is 65 nanometer. We're doing 45 nanometer designs as well. How do we go about it? What are we going to do? Should we build a traditional out-of-order execution engine? Well, that has an inherently centralized point of control, where we have to broadcast, deal with data dependencies, forward ready signals, lots of structures that grow quadratically. It relies heavily on content addressable memory, which dissipate a lot of power. It impacts cycle time. All these structures need to be visited quickly. It was very hard to verify. We did the experiment. We spent hundreds of millions of dollars on this project. So I'm not saying this out of a book, even though Dave's book is great. So as a note that it will be interesting to you, comparing cores, Dave mentioned, if my animation ever happens, mentioned UltraSpark 1. I don't know why this is not coming out. But so I took die photos of UltraSpark 1, 3, and 5, which are 3 generations of pipeline. There we go. So these are chips, but I just wanted to illustrate the difference in size. And interestingly enough, there was an alpha paper that had the same ratios between EV5, EV6, and EV7, or EV7 and 8. So the data is that the AltaSpark 3 core, even though I'm showing chips, it was 3 times as large as the AltaSpark 1 core. And the AltaSpark 5 core is another factor of 3. And obviously, we never got 9 times the performance or 3 times the performance. Going from this tapered off at 400 megahertz, this started at 500. So in the same process, I'd say we probably got 33% more clock rate. Bigger caches, certainly not ever approached 3x in performance. And same thing here. So the industry was just in this trajectory of that didn't make much sense. So we ended up canceling this. And I can guarantee you the power was a lot more than the AltaSpark T1 or Niagara. The other thing about 000 is that I mentioned this miss rate. So the largest window, somewhat flat instruction window I've seen is 128 instruction deep. And by the way, everybody cheats. It's never a flat window that you can execute any instruction that's ready in there. It's usually colored because it's very hard to build circuits that would scan this window of instructions in a single clock, get the instruction ready to be issued. But now remember that rule of thumb. Here comes a load to register 7, a use to R7. An out-of-order execution engine will continue, and hopefully will hit another load miss. But given this 1% miss rate per instruction, the probability that you hit another load in this short window is actually so-so. Fortunately, there is some clustering of load misses, so you will hit more than the average. Main memory is at least 500 cycles away, at least in this generation, and a large SMP even further. So 127 clocks later, you're done, right? So you'll be idle for more than 300 cycles waiting for main memory. So ideally, what the academia is doing and research labs, that boy, wouldn't it be great if we had an instruction window that was covering main memory latency and yet would not impact cycle time, area, power. So very difficult, but that's what I'll describe now. So the key idea is that we're after multi-threading, multi-core, no doubt about it. But can we use those structures to accelerate or to simulate what a large instruction window would look like? And that's what we're doing. Because if I stood here today and explained all of this and said, well, that's all great, and I can only put one of these scores on the chip in 65 nanometer, we would have failed. We need to put tens of these per chip. So the hardware scouting idea is that in hardware we launch a thread under the hood as soon as we detect there's a load miss, and we send that hardware thread down the path of instructions. It follows instructions, it follows loads, it follows branches and tries to hit the next landmines, if you wish, the next load misses, store misses, and bring in all interesting instructions and data into the processor, so that hopefully, when the data comes back, then the thread resumes and just flying, running at cache speed as opposed to main memory speed. So there's related work. We've been doing what we call assist processing for years at Sun in the MAGIC program. Run ahead has been a term that is very similar to this. Speculative pre-computation. Here I'll give you some real data and real microarchitecture support to complement this. First of all, is this a good idea? Does it work well? So we do our homework. We run your favorite benchmarks and applications. And first describe, well, I guess I should show the chart with the misprediction. I guess I didn't show. If this branch is mispredicted and we're in scouting mode, the scout will go down this path, and then 5 cycles later we'll find out that there was a misprediction branch. Comes back, goes down this path. No big deal. It's only in the case where you don't have the data to resolve the branch that you run into issue. So I may have gone down here, and if this branch depends on the original load miss, then we're speculating, we're prefetching down the wrong path. And then we asked ourselves, well, should we stop the hardware scout or should we continue? And it turns out that even if you mispredict, it was kind of a wash because code is structured in such a way that, well, then you'll have a merge point later on. Then you're really prefetching interesting things. Maybe it's another iteration of the loop, and now I'm finally going on the other side. And the thing to keep in mind, and also scares people about this, is that, oh, you're going to pollute your caches. Well, we'll be very happy if we bring 5 cache lines through this mechanism. We'll be very happy if we hit 5 load misses or store misses here. An L2 cache will have 10, 20, 25,000 lines in there. So we're not really creating much pollution through this because we turned out to be quite accurate. As this shows, this is our worst case example. This is running a large database application. These were the branches that were resolved and predicted correctly. Great. These were, we didn't have the data, but we predicted them correctly as well. So this is all fine. Here, we mispredicted the branch, found out a few cycles later, repaired it, came back. So only in this case here do we run into potentially prefetching wrong data or instructions. But that seems to be just 10% of the time. For integer benchmarks, that was only 5% of the time. And for floating point, you basically don't mispredict the path of the hardware scout. So far, great. The scout seems to be very accurate at doing what it does. Now, that's interesting, but how far can you go? And the key observation I'll give you here is that the scout actually rips through instruction faster than a normal thread because it doesn't have the same constraints. I could have like 3 floating point divide in the same clock and issue all 3 of them because we don't really care about the result. And even data dependencies. If I have a load that its address is based on a miss, so we propagate this not there bit. So we can issue that load, and it can even issue the dependent usage of that load in the same clock cycle. So the scout just rips through. And the name of the game, one time I was discussing this with Guri Sohi, is that he or she who gets the next load miss wins. And that's the goal of the scout, is getting that heavy leverage of 500 cycles, trying to erase that. There's so much benefit in doing this. So we did some kind of like a histogram showing the scouting distance. So this is for database, and me do a log chart. But this is number of scouting events and their depth in terms of cycles ahead of the main thread. And it goes from 0 to 1,000 cycles. So notice that we go very deeply. So these are all events that are hundreds and hundreds of cycles ahead of time. We can show it a little bit better. This is running integer benchmarks, and you see 3 zones basically: L2 cache, L3 cache, main memory. And same thing for floating point. You see the 3 zones again. That effectively the scout is able to go very deeply. That's all great. What does it buy in terms of performance? So we simulated 2 processors, one in a traditional out-of-order execution engine in red without the scout, and one in blue, an in-order pipeline actually, with the scout. And we varied the level 2 cache. So what it shows is quite interesting, that given a small cache, half a megabyte, the scout was buying you 40% performance over the traditional out-of-order execution. So you have a more simple pipeline and yet higher performance. Notice I've picked intentionally a fairly small cache. Obviously, we have chosen to dedicate silicon area for cores. So if you look at Niagara as a 3 megabyte L2 cache, divide this by 8 cores or 32 threads, basically have a pretty small cache per core or per thread, even worse per thread. If you look at it in a different way, you can say, well, if I have a 1 megabyte cache, how does that behave? Well, it behaves like a traditional processor with an 8 megabyte cache. So we're trying to use the silicon real estate for, smart techniques to buy back some of the cache real estate that we lost. And if you look at 4 megabytes, caches have a diminishing return as well, and you buy yourself 12 megabytes. On integer benchmarks, well, you just don't miss that much with integer or spec in, certainly. So it still buys, 11% performance, or effectively doubles the cache. And somebody will point out, well, what's this asymptotic behavior up there? Well, the Scout does better than an infinite cache. Well, it does so because we actually bring the data in the L1 level. So if somebody was blindly dedicating, silicon area for caches, that would be the wrong thing to do, because you'd much better bringing it into the low level of the cache hierarchy. So in a floating point, even more spectacular results. No, we're not going to have a 24 megabyte L3 cache in 90 nanometer and even 65 nanometer, but we're buying ourselves that cache back, as opposed to, like Montecito is a phenomenal L3 cache, but is that the smart thing to do? And as you know, caches aren't the ultimate answer. Cold misses, shared misses. So we easily see 50% of misses being shared misses. So a cache, you could have an infinite size cache, you'll still have all these misses. And as I'll show, it gets worse than that. This is a window termination condition. So why does a window fill up? This is a 16 deep window, 32 deep, 64, 128 deep. And part of it is, well, yeah, the window itself fills up. I just have 16 instructions and it filled up. And as you increase the window size, that happens less and less. Misprediction branches are important. But look at the serialization. So you ran into an atomic instruction, a lock acquire, a lock release, that forced us to flush the instruction window. Can't speculate beyond that. Well, that's all gone if you have an implementation that does scouting. We can go through locks. You can go prefetch the lock. You can go prefetch the loads and the stores beyond the atomic instruction. So now you're just left with, mispredicted branches and iCache misses. So, very powerful model, and we hope in the next few years to be able to quantify that even more. So, we're rapidly shifting the entire product map based on some of this technology. The scouting is not in Niagara or the AltaSpark T1. It's in our 65 nanometer product called codename Rock right now. We're gradually disclosing some of the technology. Some of you will point out that, okay, hardware scout is great, but it's just a prefetching thing. You have a runtime oracle, kind of. Well, we actually do more than this. So I'll leave it at this. And some of you that have explored thread level speculation, we did a lot of work on this. Called space-time computing. It was mostly based on Java thread level speculation. We're still pushing this even beyond what we did in space-time computing. The big dilemma we have is, on the server side, there are lots of threads out there. So the decision for an operating system or a load balancer software is, do I allocate hardware to speculative work, or do I just allocate hardware for 5 more Google searches? So from an energy standpoint, you're better off not doing the speculation. But if we get to a model that, boy, this customer is paying the big bucks, and we're going to give him hardware, and we'll accelerate his or her workload by another factor of 3 by giving them 3-4 cores or 3-4 threads, and then we'll do speculation. So that's the space we're exploring here. And we're also providing hardware structures to accelerate Java. So this is everything I've discussed so far is 100% Spark binary compatible. Yet, what can you do given that so we invented Java? We have lots of engineers building virtual machines, all kinds of virtual machines, and we would still like to run Java apps as fast as possible. So, the hardware guys and the JVM guys, we meet and analyze applications and pinpoint this generation's bottleneck. And typically, we've identified garbage collection as something we need to address, especially for real-time applications. So you want to have guaranteed pause time, and also synchronization again. So it's one thing to have all the threading. Threads are beautiful in Java, but at some point you run into these serialization, and it'd be nice to accelerate the locking mechanism. So we are doing all of that. It would be a shame if we didn't. It would be a shame if we didn't take advantage of the fact that this is all under the hood and does not break the Java compatibility level. So in summary, mostly focused on processors today, but at the end of the day, it's at the system level. I tried to show some of the trade-offs between cores, threading, system-level issues, the price-performance level. Reliability, just had a discussion with Dave on this, very important. The fact that we're consolidating cores in memory means we have a lot less parts in our systems. And if you start with a tenth the number of parts, boy, that does a whole lot for your reliability. So stay tuned for seeing more and more technology being described under the umbrella of throughput computing. And I'll be happy to take any kind of question you might have. Thank you. Yep.
I got a question. So you got this processor with bank memories, bank caches. Are the compiler people working on things like vectorization, vectorizing across the different core threads?
So I'm very excited about this because, yes, we've been working on auto-parallelization for 25 years. We've been looking at vectorization along the lines of some of the research done here. The fact that cores are so much closer, plus the fact that, we will have lock acceleration, the scouting, means that the economics of parallelizing things are a lot better. So if you look at our scores right now that we post on OpenMP and what we get from 2 and 3 and 4 processors, they communicate that it takes us 300-400 cycles to communicate. So we're getting interesting improvement, but modest in what we can do with CMT. So the cores are a lot closer. We can communicate a lot faster. At the thread level, they communicate to the L1. So we can really take advantage of things here. So the other part I will say is that we are one of the 3 companies working with DARPA on supercomputing, the DARPA HPCS program. And HPC is a big target for the Spark world as well. And we are proposing an architecture that's based on some of this.
Oh, really?
Yes, yes.
And the compilers people are going to be working too?
Yeah, to make that work well for those workloads.
And will it be like OpenMP style parallelization or?
Well, I'm not sure how public we've gone with this, but it's interesting that a community is strong, right? And because of the availability of low-cost clusters, MPI now is parallel, is very common and very popular. So now MPI has become part of the requirements for a next generation. yeah, but you see what a community will do to you, right? So similarly, why have we been doing clusterings as opposed to SMPs? Well, it's because SMP manufacturers we've been building expensive systems to deliver that SMP. I believe we can build cheap SMPs. So, and hopefully the programming model hasn't gone too far that we can still seduce people from, boy, wouldn't you like to have a a nicer programming model, and hopefully yes, and then if the price performance is attractive, people will buy those machines. Yep.
Well, there's a lot of C code that was written in the era of static pipelines. That's what you had me as. Then, fast forward, all students who were undergrads, they never had a static pipeline machine. I guess they kind of grew up without a word and knowing one. When you take a look at C code from the era of static pipelines and C code from the out of order and learn on stuff like that, do you see the difference right away?
Okay, so the number one observation I'll give is that I am looking forward to the industry and academia to develop metrics that measure how robust a processor is or a pipeline. And robust in the sense that how well does it do on old code? How well does it do on compiled code that wasn't compiled with the latest, greatest flags? How well does it do on code that was tiling the data set for a cache that's slightly larger than what you have? And our example is when we introduced AltoSpark 3, pretty nice pipeline, but initially needed a lot of compiler attention. And the compilers were not yet up to par, so it didn't do great on existing code. Now, very conscious about this. Commenting on two processor nodes here. Niagara, not very sensitive to the quality of the code, because it will interleave. It will just, the way I've described this is a little bit simplified, but Niagara actually round robins every clock cycle. And if a load use was scheduled for 1 cycle and now it's 2 clocks, another instruction from another thread will be scheduled in between. So in that case, it wouldn't matter much. For the rock node, we're very conscious about this, and we're putting bells and whistles to be able to kind of do in hardware what some of the traditional would do, but in a totally different way. But yeah, very important. So, and honestly, you wouldn't want to expose it to programmers, ideally. It would be nice to abstract most of that. Dave?
Competitors, when they ask them about Niagara, they said, well, the kind of 2 things. Well, that's easy. It's not as hard as what we do. Anybody can do that. Kind of another, like we could slow our processor down and do that. And the kind of related question is, well, if it's a nice simple clock, if it's a nice simple pipeline, why wasn't the clock rate a lot higher? So kind of 2 sides of a coin.
Okay, so I would say the most important thing about Niagara or the AltoSpark T1 was having the courage to do it. Having the courage to say, I'm not going to care about spec int to spec FP. I'll care about spec int rate and all these benchmarks. So could the competition do it? Absolutely, but they'd have to start from scratch, right? Right now, if they turn down their core frequency, well, they'll still put only 2 cores in 90 nanometer. I expect both coming from Intel and AMD that we'll see quad cores in 2007. And 2000 in 65 nanometer, because the dies, the cores are big, they burn a lot of power. And then the beauty of the whole thing is that take these quad cores in 2007. Guess how many load misses that will support? The windows are 32 deep, so you'll have 1 or 2 load misses per core. You'll have like 6 to 8 outstanding loads coming to the memory subsystem on average. You have 32 right now in Niagara and 90 nanometers. So I think, yes, the barrier to entry, people can build these things, but it was, starting it 3 years ago was the key. And now, of course, we're not standing still. We're enhancing the product line. The other key to the Niagara program was time to market between tape out and system ship. And I would say this has gone as well as AltoSpark 1, even though there are more process steps, and it takes us a while to get the chip from tape out. But I said big reason for that was the methodology and the fact that we didn't have dynamic circuits. We didn't have a deep pipeline. The pipeline is very simple. I think that all bought us verification time and even post-silicon time because we didn't have too many bugs. So the clock rate has been announced as 1.2 gigahertz. We did simulate 1.5. 1.5 wasn't buying too much. If we could have run at 2.2, I'm sure we would have seen performance improvements, but the power would have gone up significantly. So I think that factoring time to market and the methodology was probably the right decision.
Right.
All right, thank you very much.